I'm sure we've experienced this one time or other in our lives. You're sat in a hotel room and you're really bored. You're skipping through the TV channels using your remote and you can't find a single thing to watch. And then you start thinking to yourself, if only I could see my own TV at home. Maybe there's a sports event going on. Maybe there's a movie that you can pick up from your subscription. Maybe there's just something on your DVR that you recorded the other day that you'd like to watch. Well, up until a few years ago, you could have done that. This device is a SLINGBOX, and what it used to allow you to do would be connect your set-top box video output into it, and it would then send that signal over the internet and you could just watch it within a browser no matter where you are in the world. It was brilliant. But unfortunately, Sling Media stopped this service in November 2022, and so since then you've not been able to do that anymore. Well, using a couple of Raspberry Pis, a USB capture card, and a little bit of know-how, we can replicate that. Let's go and take a look at how to put that together right now. Greetings techno nerds and Pi geeks everywhere around the world. My name's Jeff. I'm an IT professional who's been in the industry for 30 years. In my spare time, I love making little projects with Raspberry Pis, and I'm sure that you do too. If you like what you see here, please click that like button and subscribe to my channel so you can see more, and then click the notification bell so you can be notified when I put out another video. In this project, we're going to be replicating the functionality of a SLINGBOX. Let's go and take a look at what we need to do that. First off, on the left, you can see my set-top box that's fed by a satellite dish. The output of this is then fed into a USB capture card that I plug into a Raspberry Pi 4. It has to be a Raspberry Pi 4 because it's got USB 3 ports, and only the USB 3 ports have enough bandwidth available to allow the video signal to flow into the Raspberry Pi. On the receiving side, things are much simpler. All I have is a Raspberry Pi 3 or above, and all I have to do is connect the HDMI output into the TV of wherever I am. Now, the USB capture card that you use for this project can be any device that is capable of capturing a full HD signal at 60 frames a second. As long as it fulfills that, everything's fine. In the description below, I'll put a link into the device that I use, but please don't feel like you have to use that one. Do shop around. There's a huge variety in these devices, all kinds of prices, so just pick the one that's good for you. Now we understand the hardware that you need for this project, let's go and take a look at what the software stack is going to look like. Now I'm going to use this same software stack on both the transmitting side and on the receiving side. The first thing you'll see at the bottom here is Raspbian Buster. Now this is a slightly older version of the Raspberry Pi operating system, and I have to use that because OMX Player, which is the player software I'm going to use, has since been deprecated in favour of VLC. However, I've not been able to get that to work just yet, so if I stick on Buster, everything works just fine. The next thing that we'll layer on top of there is a library called SRT. This is an open source library provided by a company called Haivision, and it's a great protocol that allows you to transmit video with very low latency over the internet. It also provides great value add like encryption and error correction, and this helps to ensure the integrity and reliability of your video stream. The next bit of software I'll be using is called FFmpeg, and this is a wonderful piece of software that's often referred to as the Swiss Army knife of video processing. It's entirely open source, and it allows you to do any kind of video processing task that you could ever really need. In our case, we'll be feeding our video capture device's signal into FFmpeg, and that will then be using SRT to send out the video stream. The last piece of third-party software that we're going to be using here is OMX Player. As mentioned before, you can't really get that anymore in the new version of Raspberry Pi OS, but that's okay, we can still use it in this context. It's a great video player that exploits the hardware acceleration that's available within the Raspberry Pi to decode the video signal and display it directly onto the screen by hooking into the Raspberry Pi's GPU. As well as all of that third-party software, there are also some scripts that I've had to write in order to make all of this transmission and receiving of the video stream work. Let's go and take a quick look at that now. This script runs on the Raspberry Pi 4 transmitter, and the first thing it does is it takes in some environment variables to configure it. The first being a port that it will listen on in order to handshake with the receiver, and the next two are descriptors for the audio device and the video device that it has to use to capture. The main loop of the code is down the bottom, And all it does is it waits for a connection from the receiver. The receiver will then give it a port number to use for the video connection and also a password to use for the connection. That way, every stream that's generated out of the transmitter can use a unique password and be impossible to hack or intercept. The main guts of the script are in this run ffmpeg function. Firstly, the port and the password are extracted from the information that's passed in by the receiver. It then calls into ffmpeg, and these rather complex lines here just define how the audio and the video will be captured from the USB device. Now in the middle, there's this ITS offset option. This is used just in case the captured video and audio are actually out of sync with each other. The two streams do behave completely independently, so this can happen. In this case, on my system, I've ended up with a 0.3 second delay between the audio and the video, so I've got to correct for that. These lines down here define how the stream will be output. In this case, I'm outputting the audio first and then the video. This way, there will be a small 0.3 second delay between the audio and the video. And so everything will be output beautifully synchronized. The H.264 OMX option that you can see just at the bottom there references a really neat little party trick that the Raspberry Pi has. Built into its GPU is a hardware encoder for video, and we can use that to encode our video stream while having a very small effect on the CPU. The last line of the ffmpeg command effectively wraps up the video and the audio together and then generates our SRT output. You can see there's also an option to apply the password that was provided earlier. On the receiving side, things are much simpler. Initially, I create what's called a FIFO queue in order to receive the video frames. Now this is a special type of file on a Linux file system where you can drop data into it and you can read that data from it, yet the actual file on the file system never grows at all. It's just entirely dynamic. The next thing I have to do is provide some configuration information. In this case, the name of the host that I want to connect to, the transmitter, the control port that I'll use to connect to do that initial handshake, and then the port that I'll use for the actual video content. The next line actually generates the password. In this case, it just generates 10 characters randomly and uses that, so it's really nice and secure. Within the main loop of the application, the first thing that happens is that it connects off to the host and provides it with the port number that it wishes to use and the password. After that, it calls into an application called SRT Live Transmit, and this is provided along with the SRT libraries from Haivision. That gives you a really simple mechanism to hook into an SRT stream and extract the video frames that you get from it. In this case, I just write the video frames out to our FIFO queue. Once the video frames are coming in, I then use OMX Player to capture those video frames, and it just outputs them straight to the HDMI port of the Raspberry Pi. For as long as OMX Player is receiving video frames, it will continue to run. Once it doesn't receive any video frames anymore, it will just exit. When it does, we do need to kill off the SRT Live Transmit application, and that's what this last line does here. After that, it just sleeps for 5 seconds and then loops round again. So what this means is, if the transmission gets interrupted in any way, it will recover itself. Now I'm going to be packaging up each layer of this software as a Docker container. If you're not familiar with Docker and have never heard of it, do take a look at this playlist that I've put together that describes what Docker is, why I love it so much, and how to use it on a Raspberry Pi. I'm also going to be using a bit of software called Docker Compose, and this makes it really easy to define what containers you want to run and any configuration options for them. Here you can see a Docker Compose configuration file that I'm going to be using on the server side. What this defines is the image that you're going to run. So this is the ID of the container. You then give it a name, and then you provide it with a list of all the ports that are going to be exposed out of that container. In this case, it's going to be 2. One for the original handshake and one for the video stream. After that, I provide the environment configuration and also the type of mode that I want the server to run in. I'm going to use the same container on both the transmitter and on the receiver, and I'm going to have another script that will decide which of those scripts that I showed you earlier are going to actually run. Now for the transmitter, it also needs to know the devices that are going to be required in order for it to work. In this case, it needs to know the GPU of the Raspberry Pi, the the sound device and the video device that are going to be captured. If we look at the equivalent compose file for the client side, it's a little bit simpler. Again, I'm referencing the same container, and I'm going to give it the same container name. It's running on a different box, so this won't really matter. I then give it the host name that the transmitter is going to run on. And please don't bother trying to hack this. This host name is going to be torn down as soon as this video is complete. I then provide it with the control port that's used to negotiate the connection, and also the video port that the video stream will run on. And just like on the server side, I provide the run mode that the script is going to run in. Just like on the server side, I need to provide devices that OMX player can actually play out on. Again, the first one's the GPU of the Raspberry Pi, and the second is the system sound device. Now we understand all of the software that's going to run on the machine, we can go ahead and build it. Now I'm going to build it on the Raspberry Pi 4 that I'm going to use as the transmitter. It just makes life easier. So here I've got a session on that. So let's go ahead and start building the software. We're going to build the software layer by layer, and we're going to start with the Raspbian Buster container. It's built using this command here. Now it looks quite complicated, but building Docker containers is really quite straightforward. The -t option defines how you want to name the container, and the -f option specifies the name of the Dockerfile that it's going to use to perform the build. If you're not aware, a Dockerfile is just a list of instructions to run on a given container in order to build it up. The last dot just says to run all of this in the current directory. Let's kick that off now. And it's going to take a little while to run. So while it does, let's go and take a look at the Dockerfile and see what it's doing. The first thing I do here is grab a pre-existing Raspbian Buster image that's available over the internet. Now, whenever you're doing anything with Docker, it's always worthwhile just seeing if there's a container you can already use. There's no point in reinventing the wheel. Now, this particular image doesn't already have a Pi user created on it, so I want to create that user group and that user. I then create a home directory for that user. I change the ownership of that home directory to the Pi user, and then I change the password, so I just provide it with the default of Raspberry, just like Raspbian always used to. The last thing I do is provide a whole bunch of group membership to the user, so that he's able to do everything that I need. After this, I then just remove any packages that aren't required anymore, and I just clean up. If we switch back to our build now, we can see that that is completed. So the next thing to do is to build the SRT container. Let's go and kick that off here, and then we can go and take a look at its Dockerfile and see what it does. Now this is a bit more complex than the last Dockerfile, as you can see. However, it's not really that complicated. It uses that Raspbian Buster container as its base, and on top of that it installs a whole bunch of prerequisite packages that are required for the SRT build. It then switches to become the user Pi, and then moves into the home directory for the user. It then creates this source directory that it will use to download the SRT source code into. It then calls into Git to download all of the SRT source, and then it runs the provided scripts to make the library. Once that's finished, it becomes root and then runs make install in order to install all of the libraries into their runtime locations. When all of that is finished, you have to run ld-config to make the system aware that the new libraries are available. Just like with the Raspbian container, I then clean up a little bit. I then use a multi-stage build, and what this does is ensures that it's only the end result of the build process that ends up getting written into the container. Where the source directory was originally created and all the source code was pulled into it, even though we subsequently delete that during the cleanup process, Docker still has a memory of all of those files existing. Using this multi-stage build process, I ensure that only the result ends up within our final container, and this reduces the overall size of the container at the end. Now let's switch back to the build and see how it's getting on. This is going to take a while, so let's just skip through to the end. Now that the SRT library is built, we can go ahead and build ffmpeg. Very similar command again. So again, let's go and kick that off and then go and take a look at its Dockerfile. Now this one, again, it builds from the SRT library as a base, switches to the user Pi and goes back to its source directory. Here it pulls two pieces of source code from Git. The first is all about hardware acceleration support, and the second is the ffmpeg source code itself. The first thing I do here is I make ffmpeg aware of the SRT library and where those files are. That's configured in this ffmpeg srt.conf file. After this, it just goes off to the userland source files, and then it just runs the command to build them. When that's all finished, it updates the library configuration on the box, and then it goes off and it builds the ffmpeg libraries using these commands here. When that's all done, it becomes root and it runs make install to put all of the libraries onto the system where they can then be picked up and used. Just as before, I then perform some cleanup and ultimately do another multi-stage build, again just to ensure that the size of the container is minimized as much as I possibly can. Now let's switch back to that build and see how it's getting on. Again, like with SRT, this is going to take quite a while, so let's just skip it through to the end. Okay, now that's built. The next part is to build our OMX player. So let's go and kick that off. And once again, we can go and take a look at the Docker file that's used to create it. Now this one is really quite straightforward since OMX player is already available as a pre-built package. So all we have to do is take our ffmpeg container, become root, install OMX player, run ldconfig, and then we're done. So let's just go and see how that build's getting on and wait for it to finish. Now that's complete. The next stage once again is just to build the final container, the PiTV TX one. Let's go and take a look at what that has. So this container just builds on top of the OMX player container we just built. First off, it installs a tool called netcat. This is a really useful little tool that just allows a script to just listen on an arbitrary port for a connection, and then you can transfer data up and down that socket. I then add in the client and server scripts that we looked at earlier, and then it also adds this run.sh script. This is nothing particularly complex. It's just a small script that runs on the box, and it's basically told what mode the container is going to run in. If it runs in client mode, then it runs the client script. If it runs in server mode, it runs the server script. If it gets told anything it doesn't know about, it just bombs out. Really simple stuff. I then have to update the permissions on all of these scripts so that they have execute permissions. This just means that they can be run. The last thing I do is this strange entry point command. This defines what gets run at the point where the container starts. In this case, it will run that run.sh script. Now let's loop back to that build and just see how that's getting on. Now this is complete. If we look at all of the images that exist on this particular Raspberry Pi, you can see all of our different containers that we've just been building, ultimately finishing in our PiTV TX container at the top here. Now we need to copy this container off to the receiver box, and that's actually really simple to do. All we need to do first is actually save the container contents out to a file, and this is what I do here. The file is fed through gzip in order to ensure that it's compressed at the end. So let's just run this now. Now that the file's saved out, I can just copy it onto the other Raspberry Pi, the receiver. I can just use the SCP to do that. Now the file's copied over, all I have to do is log into the receiving Raspberry Pi. Move into the directory where the file containing the Docker image is, and then I can load it into this Raspberry Pi's local container cache with this command here. Okay, now the container is copied over, copying over the Docker compose file. I've copied that into the user local bin directory, and I've named it as pitvtx.compose. I've also done the same on the transmitting side as well. So now we have all of our software built, it's been deployed onto both of our Raspberry Pi boxes. Now we're finally able to see this thing in action. Let's go and take a look right now. What you can see in the top left panel here is the output from my set-top box. On the top right, you can see the output from the receiving Raspberry Pi. And then in the bottom, you can see terminal sessions to each of the Pis. So first off, let's go and start up the server on the transmitting side. I'm just doing this using Docker Compose. And now you can see it's just sat there waiting for a connection from the receiver. If I start up the receiving side now, using exactly the same command, the container will come up, it will do its handshake with the transmitter, and then you'll see it start the video stream and it will start playing it out. Now this is brilliant, and as you can see, there's about a 1 second delay in between the transmitter and the receiver, which isn't too painful. Now this is all great, but it's all a little bit useless if all you can do is look at one channel. You really need to be able to control the set-top box somehow. And so what I've done is I've created a little web application here that I can use to control my set-top box. What I can do here is just click on the buttons and it will just behave exactly as if I was just pointing the remote control at the box. And there you can see I can just change a channel really easily. Now, just to avoid any copyright issues, I will just go back to the Sky preview. But you can see that the remote actually works really well. So how did I achieve this? Let's go and take a look at the source code for this, and I can show you how it all works. The software is written in Python. I use a framework called Flask that allows me to easily create a simple web service using normal REST verbs. The main route defined here responds to both get and post verbs. If you request it with a get verb, it will render this template called remote.html. This just provides the basic web page that displays all of the various buttons. For each one, I then provide it with the code for a remote control signal. Now these remote control codes are all referenced from a library that is available in GitHub called PySkyQ. Now I happen to have a SkyQ set-top box, and this library can be used with any model of that in order to control it. All you have to do is give it the IP address of the set-top box and the remote control code that you want to send, and it will then send that remote control code to the Skybox and it will do its thing. There are a number of these different libraries available for different set-top box manufacturers, and if you just search around on GitHub or just around the internet, you'll find quite a few. But if you've got a set-top box that isn't supported by anything like that, then you might be able to use a system such as Flirk. This is just a small USB-based IR receiver and transmitter that's got an API against it. So you could use that to learn the remote control signals for your specific remote, and then you could bake those into the remote control web application. Switching back to our code, when you click one of the buttons, the value for the remote control signal is sent back into the root via a post request. All the code then does is extract the code that needs to be used and then calls into the library to virtually press the correct button. As you've seen, that works really nicely, and I've been able to control the SkyQ box really effectively. However, that little 1 second delay, that may irritate a few people. So what I've done to work around that is I've applied another layer that you can see here. This time it's based upon channels, and when you click one of the buttons, it will actually send a collection of remote control commands off to the set-top box that are required to switch to that specific channel. Now, depending on what you're looking at on your set-top box, just pressing the numbers may actually do different things. So when I do this, I also make it go to the main menu and then back out again. That way I can guarantee, no matter what you're looking at on your Skybox, at the point where you hit one of these channel buttons, it will ultimately end up in the right place. Now again, just to avoid any issues with copyright, I'm just going to bring back the original remote and switch to the Sky help page. Now, one thing you may be thinking here is that this is all great. I'm running across my local network, and so obviously things run really nice and quickly. But what about if you're in a completely different country? How will it work then? Well, we can use a VPN to go and take a very quick virtual journey to a different country, and then we can see what the impact is. So let's go and take a look at that. Now, the first thing I'm going to do here is just stop the receiver software. Now that that's shut down, you can see that the server side has just gone back to waiting for a new handshake connection. On this box, I've got a second Docker Compose file. What I do is I define a new container that actually runs up a VPN connection. And within that, I then pass that network connection to my other container, so it ends up running within that VPN. And now on the receiver, if I start up that Docker Compose application, it first starts up the VPN, and then a few seconds later, it will then run up the PyTVTX container. You'll see it just establishes its connection to the transmitter, just like normal, and then gets the video stream. You can see in the output at the top that the latency is really not any worse. And just to prove that I'm not cheating, there's a little script I can run here. Now this may look quite complicated, but all it's ultimately going to do is just run a web request that will return me the location of where I am in the world. So now I'm running that inside the PyTVTX container. So the first thing it's going to do is just download a tool called curl. This just lets me from the command line issue web requests. It's called into this API, and now you can see that the return from that is that it is indeed running in New York. So if I were in a hotel in New York right now, this means I could quite happily watch my home TV from my hotel room and change channels and do whatever I like. It's really a very powerful system. So there you have it. We can now watch our TV abroad, and we can control it using a virtual remote control. There is just one last thing that we want to do though. We don't really want to manually have to start up the software every time that we want to watch something. So we can do that by using services right there in Raspberry Pi OS. Let's go and set that up. The first thing I'm going to do here is just shut down our connected system on both sides. On both of the Raspberry Pis, I've created this little file. It's what's called a service definition, and it just provides a mechanism to automatically start up and shut down software. Within this exec start section, you can see that I just issue the command to Docker Compose to start my application up. Equally, when exec stop is called, then it shuts down the application. If it crashes, then the service is set to always restart automatically. Now to enable my service, all I have to do is type this command here. And then the service is available. I can then start it. And I can verify that it started successfully. If I look at the running containers on the box, then I can see that my PyTVTX container is now running. I can do the same on the receiver side. And there you see that the service has started up, and now my TV connection is there. While we're here, now we've got a command line available, we can just take a quick look at what resources are being used on each of the boxes. As you can see, on the transmitting side, it's really very lightweight. And this is all thanks to the hardware encoding on the Raspberry Pi that we can use for the video streams. We're consuming way less than 1 gig of memory. So even if you don't have an 8 gig Pi 4, any version of the Pi 4 will work just perfectly. On the receiving side, things are similarly light. You can see there's very little CPU load and also very little memory being used, yet everything is running perfectly well. The net result of this is that you could also have your Raspberry Pis doing other things as well, not only running and watching TV. So that's everything for this project. Next time you go on holiday, all you have to do is take a little Raspberry Pi with you and you can watch your home TV anywhere you like. All of the Dockerfiles, source code, scripts and everything that you've seen today is all available in my GitHub, and I've linked to that in the description below. Thanks for watching this video all the way to the end. If you've got any thoughts or suggestions for other projects I can do in the future, please leave a comment. Also, if you like this video, please click the like button, subscribe if you want to see more, and click that notification bell so that you're notified when a new video becomes available. But that's everything for this project, so until next time, bye for now.